Okay, so now we've done two different models, one with SATV in and one without SATV in, and it turns out that we can actually do everything that we just did sort of by hand. We can do with ProcGLM Select. ProcGLM Select is a fairly new procedure in SAS, and I'm still learning all the capabilities that this procedure has, but it's pretty powerful and pretty cool, as you'll see. So if I run this in ProcGLM Select, I already have my code set up for this, and you'll see that I'm fitting GPA, high school GPA, HU, weight, and SATV, just like we did before. I'm calling in the training data set and also telling SAS that my test data are my testing data set, and I'm asking for an ASE, average square error plot. I'm not doing any selection here. I'm just going to have SAS run this. Look at what we get. So there's the model, and note again, this is with the model estimated from the training data. So again, we get SATV as non-significant. Okay. Remember, we had 118 observations in our training data. But we also get this cool plot. And this is the average square error on the y-axis. And recall what we said up above for the when we saw that generic plot up here. This is really what we're looking at here. Instead of mean square error on the y-axis, we have average square error. But again, we have the training model, and the testing model. And that's what we're looking at here in SAS. So we have our training model in red, or our training model in blue, our testing model in red. And notice that for these four variables that we've included in the model so far, they're both decreasing. And so that's good. And notice that we have the ASE and the test ASE, and for the model that has HSGPA, HU, and weight in, the test SAE is 1.143, just like we calculated it in our notes. And for the model that also includes SATV, the test ASE is 0.139, again, just like we calculated in our notes. So it's the exact same values that we calculated. And now we can try adding all of the potential explanatory variables in the data set. And order here matters because GLM Select is going to look at the variables in the order that we add them. So I'm going to add those 4 variables that we've chosen first, and then the other variables, SAT, Math, Male, I forget what SS stands for right now, but first generation, number of social sciences class or credits, first generation, and whether they come from a high school that sends a lot of students to college. And watch what we get if I run this. Here's our average squared error plot. And again, note that the average squared errors both decrease up through the SATV model. It's hard to tell if they're decreasing or pretty much staying the same for the SAT Math, if we add SAT Math to that same model. But now look what happens. Once we start adding these other variables, Male, social sciences, first generation, college bound, the average square error for the testing model starts to increase. So again, the way to interpret this is that over here in this part of the model, or in this part of the model building, we're underfitting the model. Over here, we're starting to overfit the model. And then right in here is where we hit that sweet spot, somewhere in there. Okay. So what do we notice from the average square error plot? The testing ASE decreases as we add more terms. Up through the model containing SATV, okay, but starts to increase after that. And so again, I think that's a pretty cool graph to look at because it shows you which terms will allow for better prediction of your testing data. And then after we add more terms, the predictions of the testing data actually gets worse. Okay. And then as a final step, once we figure out which model we want to use, we should fit the model using all of our data. So putting the training and the testing data back together again in our GPA data set, fit that model. And notice what you get. We have y hat equals 0.641 plus 0.476 times high school GPA plus 0.015 times humanities credits plus 0.212 times white plus 0.00074 times SATV. Okay. And notice now, so the overall F-test is clearly significant, and each of the individual t-tests are now also significant, including SATV, using that final model. So I just wrote out that model again here. If you have some free time, this would be interesting for you to try on your own. I'm not going to work through all this myself, but you could go back through the entire process that we just did and change the seed in the stream init function. Now I'm not going to do the whole thing myself, but let's just try one thing here. Let's go back and change from Jenny's phone number. I'm going to change to my birthday. So now you can all see how old I am and when I was born. This is January 13th. So you can remember. And next year, wish me a happy birthday. So now if I run this, notice that now I would get 106 observations in the training data set and 113 observations in the testing data set. So again, it's almost 50-50. But because it's a random split, it's not going to be exactly 50-50. But you could work through that. You could change this seed to whatever you want to and work through this. And as you do, don't forget that you would have to change the equations that you're going to use to calculate y hat for your testing data. So go ahead and give that a shot if you want to. Good. So this is a very cool approach, but there are some problems with the validation approach that we just talked about. One problem is that we're only using half of our data to build the model. So we're cutting our sample size in half. We have a reduced sample size to build the model. So that's one problem. Another potential problem is that the test MSE or ASE, mean square error or average square error values, depend on how the data were split. We might just get an unlucky split, and so we might have a tough time predicting the values, the observations in our test data set just because of the way we split the data. So what's another approach that we might use? We might instead think about using something called cross-validation. And I'm just going to give a quick overview of this. We're not actually going to do an example with this. But So this first picture, cross-validation will address both of those problems that I noted above. And in cross-validation, we're going to systematically and repeatedly split the data into training and testing data sets, and then calculate an average test MSE across the replications to determine the best model. So here's what we just looked at. This is a schematic showing what we just looked at, and this is, again, what we call split halves validation. And this is what we just looked at. Here are our observations numbered 1, 2, 3, all the way up to n. So these are supposed to be observation numbers in this box. We randomly shuffle those into either the training data. The blue represents the training data that we're going to use to build the model, and the I guess, is this beige? Yeah, the beige is what we're going to call the testing data. And again, these are observations numbers, so this would say that observation 7, 22, 13, and so forth get shuffled into the training data set, and then a bunch of observations up to observation 91, say, get shuffled into the testing data set, and this is a random split. Okay, so that's what we did. Okay, and as we noticed, the problems with this are we have a reduced sample size and we have random subsets, so it's possible that we'll just get a bad testing data set that we're not able to predict using the training data set. So what else can we do? So now I just want to briefly talk about something called k-fold validation that you might hear about. And what this will do is put more data into the training set and then iterate through different testing data sets and average those together. So here's what this looks like. I'm going to talk about something called 5-fold cross-validation. So this is 5-fold cross-validation. Okay. And basically what 5-fold means is we're just going to do this 5 times. Okay. So first, we'll randomly order our data. So here again are the observation numbers 1, 2, 3, all the way up to n, however big the data set is. We randomly shuffle our data, and then we cut off the first fifth of the data, and the first time through, that's going to be our testing data, and the blue is going to be our training data. We fit our model with the training data and calculate the average squared error with the testing data. Then we throw the testing data back in, and we take out the next set of data. And that's going to be our holdout or testing data. And then we fit the model again with our new training data, which is in blue, and then calculate the test average squared error for this new testing data set, and do it again with a different block all the way through. So as you'll see, every observation is at one point used in the testing data, and every observation is used 4 different times for the training data. Okay, so this is a schematic of what it looks like, and then here's just a summary of the steps for k-fold, and this is actually for 5-fold cross-validation. So split the data into k groups, 5 groups here. So for this example, I'm using k equals 5. One group's the testing data. The other 4 groups are your training data. And then we estimate the models using the model parameters, so we fit our linear model using those 4/5 of the training data. Calculate the average squared error for the testing data, same thing that we did up above. This is calculating the average squared error. Now, then we'll do it again. So then we set the next 1/5 of the data as the testing data and the remaining 4/5 as the training data, do it again, and keep doing that. So we do that for 5 times. So we have 5 different average squared errors for each of our 1/5 testing data sets. Okay. And then we just average over those. So if we have 5 of those, we're going to take each of those, add those average squared errors up, and take the average of those. And then we're going to choose the model that has the smallest of these averages. So that's how 5-fold cross-validation works. also common is tenfold, so you might do it 10 times instead of 5 times cross-validation. It really depends on your overall sample size. Okay. You also might hear about n-fold cross-validation, which is also called a jackknife cross-validation. Where for each, so you do it where you're going to leave one out. So you do this n times, and each time you only leave one observation out. So here's a picture of it down here, a schematic, where the first time through your testing data is really just the first observation, and you fit the model with the other n-1 observations. Then you do it again for the second observation, leave the second one out, and you do that n times, so you fit n different models. If you have a big sample size, that can be computationally more intensive, but on modern computers, that doesn't really matter. And so why might you do this? Why might we use cross-validation over other variable selection methods? Model validation, hopefully I've convinced you that's important so we don't overfit the model. And that test error or out of sample error is important. We want to make sure that we're fitting new data well, that we're not just fitting our sample data. Okay. The other variable selection methods that we talked about were developed because cross-validation was computationally expensive, but with modern computers, this isn't a problem anymore. We can do fancy cross-validation methods. And compared to validation, as you just saw, each data point in cross-validation is used to both test and train the data, but not at the same time. We're always building the model with data that we're not going to use the tested data to test the model. And cross-validation requires setting aside much less data for testing purposes. It turns out, so ProcGLM Select can also do k-fold cross-validation, and I'm not going to spend much time doing this, but I do just want to show you. So here's, this is our model with high school GPA, HU, white, and SATV. I can ask for stepwise, where select is CV is cross-validation. And split equals 5 means I'm asking for a 5-fold cross-validation. I could also do split equals 10 or whatever, or split 10. I can also, so this actually doesn't do a random split, but I could also ask for a random 5 for a random split. And let me just run this and show you what you get. And SAS. It looks a lot like some of our other model selection techniques. It just steps, it's a stepwise approach, so it steps through the model. And here's the last step. So this is the model that was built. And I just wanted to show you that, so I asked for 5-fold selection. So you see that at each step, for the first one, it fits the model with 175 observations and it leaves out 44. And the same for the next 4 steps, or the first 4 steps. And then for the last one, it uses 176 observations and leaves out 43. And then down here, you can see what the parameter estimates are for each of your training models that you fit. So for the first model, with these first 175 observations, we get an estimated intercept of 0.69, 0.60, 0.57, and so forth. Here are the slopes for high school GPA that you get from all your models. And then the final estimate is really just an average across those 5. So I think it's pretty cool. Maybe that's enough to get you started with that. But I'm not going to ask you any questions about that. So I hope you enjoyed this little talk about validation and cross-validation. It's kind of cool stuff. Again, this won't be on exam 2, but I might ask about it on the final exam.